Yeah, hello. So today I want to speak about the prismatic logarithm. And so what is the aim? So let AI be any prism. And then the aims for today are the following. So first, we want to construct a natural invertible A module A brackets 1 with the following natural data. So the first is an isomorphism phi of A1, twist of it, so we want to this guy should come with some semi-linear Frobenius, so an isomorphism from phi upper star of it to not itself but to I inverse times A1. So this Frobenius is not defined on this Broglie twist, how this line bundle is called, but it has poles and one has to invert I. And I will also write Frobenius of A1 for the composition just with the canonical morphism from from the Broglie twist to the Frobenius pullback. Later. Okay, but this is not just the only data that this Broglie twist should be equipped with. Namely, it should also be equipped with an isomorphism of its reduction modulo I to I mod I squared. So this means that these Broglie twists, they lift the Broglie twists that I, for example, mentioned in the Hodge-Tate comparison. And then, furthermore, if I is just generated by P, so this prism is crystalline, then there should exist a trivialization of this Broglie twist, and this eventually this trivialization will be compatible with a choice of P inside as a generator here. And actually, we will see that actually the data of the first isomorphism and the last one determine this Broglie twist uniquely, and then the thing in the middle is the consequence. And so
under this isomorphism in point 3, what is phi in point 1?
It's the divided Frobenius where you divide by P.
Okay.
Okay, and so heuristically, this property, it forces that one would like to realize the Broglie twist as the infinite tensor product of I with a Frobenius translate of it and so on. Of course, one has to make sense of such a thing. Okay, and given the Broglie twist, one can then pass to the prismatic logarithm. And so the second aim will be to construct a natural homomorphism which is a homomorphism from the rank 1 elements in 1 plus I. So what are we? So these are the elements x in 1 plus I, such that delta of x is equal to 0. And so that's a group under multiplication, and this should map to the Brocchiesian twist. And it should satisfy the following. So phi of the Frobenius on the Brocchiesian twist applied to the prismatic logarithm should just fix the prismatic logarithm, and then the prismatic logarithm of x should be congruent to x minus 1 in I mod I squared, where of course I'm using here this natural isomorphism. And so,
can I ask about this parentheses? Is there an I missing somewhere in the right, like this composition?
yes. Yeah, thanks. And so let me give some consequences.
So what does it mean in the first property? Phi of log delta x. Ah, okay, it's the same, it's in I, okay.
So the first consequences that one has these Brocchiesian twists, so which are like the p-adic analog of Tate twists, which just means that given, say, some module over A, then we can tensor this with a bracket j, where this of course means the jth tensor power of A, and here j is allowed to be any integer. And now let me also define the Nygaard filtration on the prism, just as the Frobenius inverse of the I-adic filtration. And then one obtains natural Frobenius phi j on the Brocchiesian twisted Nygaard filtration to the jth Brocchiesian twist by sending some A tensor B to phi of A times phi of the Frobenius on this jth power of a Frobenius twist, of the Brocchiesian twist B. And so concretely this means the following. So let us assume that I is principal, and so then by I-adic completeness of A, the second point over there already forces that A, the Brocchiesian twist, is trivial as an A module. I mean, this does not give a canonical trivialization, but at least there is some. And so what we can do is we can write the Brocchiesian twist, say, as A times E, and then let us also assume that the Frobenius of the Brocchiesian twist sends this generator E to 1 over D times E. And then, okay, we get the trivialization. Okay, just the J-Nygaard filtration is then isomorphic via the multiplication with EJ to the Breuil-Kiesian twisted one. Here we have this Frobenius phi j, and this maps to AJ, and that's again isomorphic via multiplication with the j power of E to E. And then of course this composition, so how does it look like? We send n, A, just the Frobenius of A, but divided by d to the power j. And so this makes sense for all j in Z. And so now, in order to define this atomic cohomology for schemes, one can use this construction for quasi-regular semi-perfectoids, and then the usual business with first doing some left Kahn extension, and then some quasi-symptomic descent, and then by naturality of the full construction for QRSP rings, one gets these sequences, and then one obtains it then also in general.
Via A1 and E, which is the first isomorphism, 1 over E.
This one? Yes. And so here.
And also, could you say what is the first? What is the same, the first one?
There, that the Frobenius of the prismatic logarithm is the logarithm itself. So a priori, this map phi of A1 of a Breuil-Kiesian twist, it maps to I minus 1 times that thing. But of course, the Breuil-Kiesian twist sits inside here. And so if you have the phi, phi is a map with image here, and then you can also ask that it lies inside that thing and it agrees with it. And so, actually, this is something I wanted to note, that the property of this first property of a prismatic logarithm implies that if one takes looks at the image of the of phi of a prismatic logarithm, this will already so I want to say the following. So the prismatic logarithm itself, it already has to land inside the first piece of the first Nygaard filtration of A Breuil-Kiesian twisted. Now, let me set R to be given by the ring A modulo the first piece of the Nygaard filtration. And in particular, what we get is a map from R to A mod I, and it's given by sending some A, or some residue class of A, to the residue class of a Frobenius of A, and by definition of the Nygaard filtration, that is a well-defined map. And so we can use this to define a Teichmüller map, namely from the tilde of R. So these are the this is the inverse limit over the p power map of R. Okay, this of course maps to the tilde of A mod I via this map, and now the usual Teichmüller lift by I completeness yields a natural map from these p power compatible sequences to A, because these lift uniquely. And so that's the Teichmüller lift, or a version of it. And one can note the following. So if I apply if I look at the image of the p-dictate module of the units of R, so this sits inside, so this is equal to just p-power compatible systems of elements where the first term is equal to 1, so this sits inside the tilt. So then of course this will land inside a 1 plus I, right? And so but actually it will also admit arbitrary p to the n roots, and this forces actually that these elements are of rank 1. And so then what we get is the following. So we have a map from the p-dictate module of the units of R via the prismatic logarithm applied to the Teichmüller lift. And so actually this maps to the equalizer of the following two maps. So from on the Nygaard filtration on A Brocchiesian twistors, we first of all have the Frobenius, but we also have a canonical map, both landing inside A Tate twist 1. And here, okay, that's just recalling that the prismatic logarithm is fixed under the Frobenius. And so but of course we also have a map here from this guy to its reduction. Modulo I, which is I squared, and then if we take some element z here, it's mapped to the Teichmüller of z minus 1. And so, if one furthermore assumes that mod I is transversal, then I want to show later that this map is actually injective. So meaning this map on the equalizer here is actually injective. But then this observation has the consequence that if one unravels the cyclotomic trace from the K-theory of some quasi-regular semi-perfectoid ring to TC, then in degree 2 this must be given by the prismatic logarithm, because the Dennis trace, which is more or less this reduction, takes this form. Okay. Now let me make the prismatic logarithm more explicit in a certain situation, namely, let us assume that there exists a map from the cyclotomic prism to AI. And so in this situation, we see that Q to the P is an element which lies in the domain of the prismatic logarithm. Namely, it's of rank 1, okay, that's okay. But it also reduces to 1 modulo I. And note that for this it's necessary to raise to the power p. I mean, Q maps to a p-th root of unity, and so only its p-th power lies in this group. And later, I want to show the following. The Brocchiesian twist in this case we know already that it must be trivial, but one can also give a nice trivialization. It's generated by some element EA, and this element EA has the property that Q minus 1 times EA is equal to the prismatic logarithm applied to Q to the P. In other words, in the Breuer-Keesing twist, the image of the prismatic logarithm of this element is divisible by Q minus 1, and actually that's like the division of that thing by that thing gives a generator. And one can also note that just from this equation, one can see that the Frobenius on this Breuer-Keesing twist must be given by the inverse of the Q analog of P. Just because like one has to just apply once the Frobenius here to this element to see this. And so using this one can make the prismatic logarithm concrete in this case, and this works as follows. So one can write down a concrete power series, which is called the Q logarithm, and that is the following series in some variable u, namely minus 1 to the power n minus 1 of Q minus n minus 1 over 2 times u minus 1 u minus q and so on times u minus q n minus 1 divided by the q analog of n. And so yeah, let me mention the following. So this Q logarithm has its name because it's a deformation of the logarithm, and this means the following. So it's congruent to the logarithm modulo the ideal Q minus 1. And so just staring at the series, if one sets Q equal to 1, then it follows directly that this gives the usual sequence of defining the logarithm. And also another property that one can see is that actually the logarithm is a multiple, the Q logarithm is a multiple of the logarithm. But this, here one has to be careful, namely it's the following multiple. One has Q minus 1 over log Q times log of U. And so this equality is dangerous because it only holds if here the logarithm of Q makes sense. So if one has this element log Q, then one can really get this relation. And so this series is maybe not the most convenient way on accessing.
Why do you write if there?
Pardon?
Why do you write if log Q?
I wanted to start the sentence with if Q is equal to 1 then, but then I changed it.
So is this just a formal series, or it converges in some sense, or you have some, what is the meaning of this?
For now, I want to take this as a formal series. And then later I will implicitly also assume that it converges for certain elements U in, say, certain prisms. But for now it's a power series, say, with rational coefficients in the formal variables Q minus 1 and U. And as such, it's actually the unique series such that the following two properties hold. Namely, if I plug in 1, then I get 0, and the Q derivative of this series is equal to 1 over U. So it has like similar properties as the usual logarithm, but with the derivative replaced by the Q derivative. And so this concretely means the following. So log of Q, U minus log Q of U over Q minus 1 is equal to 1. So here I'm recalling the definition of the Q derivative, but then also erase the factor U by not putting it here.
So if the relation down below log QU is some multiple of log U, so this implies that formally log of U times V, log Q of U times V is the sum, is it correct? I mean, it doesn't seem to be clear from this kind of series that it sends products to sums.
So I will explain how one can check this equality. I mean, this is all happening in a large power series ring with, in particular, rational coefficients. And there, one can check that the right-hand side that I've written down there, it satisfies these conditions. And therefore, if one knows that the Q logarithm is the unique series satisfying these conditions, therefore one gets equality. And in particular, this equality then implies that actually log Q of U times V is equal to the sum of the log Q's by this formula. So that's the way how one can see that the Q logarithm is a group homomorphism, so to say. And then the relation to the prismatic logarithm is as follows. So the prismatic logarithm evaluated on some U to the P is equal to the Q logarithm of U for some element U inside A, which is of rank 1, such that phi of U is an element in 1 plus I. So note that here I'm not assuming that U lies in this group 1 plus I and then rank 1 elements, but I take this different condition. And then for these elements, one first of all needs to check, this I want not to present here, that actually the Q logarithm converges, and then one has an equality of that form. And so the proof is actually not difficult. So we know that we can write the prismatic logarithm of U to the P as f of U times EA, where EA is the generator of the Borel-Keesin twist. And then one check just that f of 1 is equal to 0, which follows from the fact that if U is equal to 1, then the prismatic logarithm is 0. But one can also check this other property, and this reduces to the statement that the prismatic logarithm is a group homomorphism. Namely, one just equates the following. So one considers Q to the P minus U to the P minus the prismatic logarithm of U to the P. That's just equal to the prismatic logarithm of Q to the P. But yes, but this is by definition equal to Q minus 1 times EA. Yes. And so this implies, when if I move this to the other side, that F, this power series, satisfies the second equation and therefore must be equal.
So this is for all the prism log, or is for just for this case?
This makes sense whenever you have given some map from the cyclotomic prism.
Okay.
And so now I want to derive a formula for the prismatic logarithm in a particular case, and for this I want to note the following. So I've used this Teichmüller lift on the blackboard over there, but actually there exists another possibility how to lift elements from R to A. So I call this new, and it should be the Teichmüller lift. For the surjection from A mapping down to R. And so the difference between this Teichmüller lift and the one from before is just a Frobenius. So Frobenius for this Teichmüller lift is equal to the Teichmüller lift from before, just from the definition, because one has a commutative diagram like this. And so now if X lies in the p-dictate module of the units of R, then one can see that the logarithm of the Teichmüller of X is equal to the logarithm of phi of nu of X. And so that's equal, because these elements are of rank 0. It's the same as the prismatic logarithm of nu x to the p. And then, okay, one can use this equality over there and write this as log q of nu of x, v of nu of x. And so this has the consequence. So if R is quasi-regular semi-perfect and an FP algebra, then and we set A equal to the prism of R, then the prismatic logarithm evaluated on the Teichmüller of X, okay, it's equal to the Q logarithm of nu of X, and so this identifies with an element in the phi equal to Q analog of P eigenspace of this prism. Okay, but now what can be done is, so in this case, the prismatic ideal is also generated by P, and so we want to relate this to the phi equals P eigenspace in that prism. But how can we identify these two eigenspaces? This is possible by multiplying with the element log Q over Q minus 1. So that's just a check, using that like the logarithm of Q to the power P is P times the logarithm, and that the phi of Q minus 1 is like P Q of Q minus 1. And so then what we see is that this element here, it maps to the logarithm, but of the Teichmüller lift nu. So I've presented this here in detail because at least I already sometimes got quite confused about these different ways how one can lift to the prism.
So the prism of R, in this case, lies over the cyclotomic prism?
Yes.
So the phi here is a phi A A1 is this, or the ordinary phi?
Say again?
I mean, the phi is the value of the phi. Is this phi A1, or is
like if I take this trivialization, then the phi is given by this formula, but then I can also multiply it, and therefore this equalizer diagram appearing here, like just the kernel of the difference of the two map, identifies with this eigenspace.
So what is the map from cyclotomic prism to A?
Okay. How should I? Okay, maybe I just, okay. If, say, R is equal to OC, so how? Okay, so first let's consider some examples. Say R is given by OC mod P, and then where you get a map from A inf of OC to the prism of R, and then inside the prism of A inf you have the element, the Teichmüller of epsilon, and then you get the map from the cyclotomic prism by sending the element Q inside the cyclotomic prism to epsilon. And so what should I then, how should I therefore argue in general? In general I should argue that I find some morphism from some perfectoid ring, and I can also assume that this morphism, that this perfectoid ring contains, is actually, what to say, it's also flat over ZP and contains the p power countable systems of roots of unity, and then I can use this example then also in general. And therefore this element log Q, it identifies with Fontaine's element theta, and Q minus 1 is also what is called mu. Okay.
Here is a logarithm, prismatic logarithm of V of B, so that P is equal to the log Q of V of B.
Say again?
Yeah, it's just in the second line. No, just it's in TP star in that state.
Sorry, I don't understand what.
Yeah, exactly. So here, the last equality, you don't have any basis here.
So what I'm using here is this equality that I've derived in this lemma there. And so I don't have this power p anymore, but I have a q logarithm instead of logarithm of psi, and I forgot maybe this element.
Yeah, and so in the lemma you're using the previous lemma that you haven't yet proven.
You mean the uniqueness of a series?
This lemma just that you're just using this one, but you said that this is later.
Yes, this I will prove later.
But you use this one in the other lemma.
Yes.
Okay.
And so I can only prove this statement after I've constructed the Borgesian twist, and so let me do this now. And so I want to actually present two ways how one can construct this Borgesian twist. The first one is due to Drinfeld, and then the other one is due to Bhatt and Scholze. And then later I want to present a construction of a prismatic logarithm. And so the first approach uses the Cartier-Witt stack. And so let me recall that like line bundles for the prismatic structure sheaf on the absolute prismatic side of ZP, that these are equivalent just to line bundles on the Cartier-Witt stack. just by this equivalence of prismatic crystals with quasi-coherent sheaves on the Cartevich stack. And actually, the naturality of this Broykiesian twist, it already implies that we want to construct a line bundle here on the prismatic side, and so it's sufficient to construct a line bundle on the Cartevich stack. And so let me also note that we have a Frobenius endomorphism of the Cartevich stack, which is induced by the Frobenius on the Witt vectors. Just because like the base change along the Frobenius preserves this condition of being a Cartier-Witt divisor. And so what we want, therefore, is a line bundle O1 in the Picard group of the Cartier-Witt stack together with an isomorphism of the Frobenius pullback of this line bundle to I inverse times itself. So where I is the ideal sheaf of the Cartier divisor given by the Hodge-Tate locus. And so first of all, let me, it's clear that like each invertible function on the Cartier-Witt stack gives like some automorphism of every line bundle, and so let me first analyze the global sections of the Cartier-Witt stack, but these are actually just given by ZP. And so the way how one can check this, I mean, one has a lot of coverings available for the Cartier-Witt stack. One can, for example, take the cyclotomic prism, but then by naturality, the global sections can only map to elements in the cyclotomic prism which are fixed by the natural action of ZP cross inside this prism, but this is given by ZP. And so therefore one can calculate the global sections of a Cartier-Witt stack. And actually this calculation also reveals that actually there cannot be any initial prism. And so now what we also want is we want to get this trivialization if the prism is crystalline. And so how can we encode this in the Cartier-Witt stack? So we consider the morphism rho, which is associated to the prism ZP with the ID generated by P, and so that's a canonical morphism from spiff ZP to the Cartier-Witt stack, and it also appeared yesterday, namely it's given by the Cartier-Witt divisor P. And from the last lemma we can conclude the following, namely, let's consider the line bundles on the Cartier-Witt stack together with a trivialization after pullback along rho. And so now, because like the automorphisms of line bundles are given by the global sections, but these are given by units in ZP, but now if we also fix the trivialization, this means that we killed all the possible automorphisms, and so this a priori groupoid is equivalent to a set. Which is good, because it specifies line bundles with a trivialization, therefore uniquely, up to unique isomorphism. And so, as an example, we can just take the prismatic ideal sheaf defines an object. Namely, we know what its pullback along rho is, namely it's the prismatic ideal sheaf in the prism ZP, but this means that this is just canonically isomorphic to the ideal generated by P, and then of course this is isomorphic to ZP by choosing the element P. And so in order to construct the Borghesian twist now, we can, it's sufficient to prove the following lemma, namely, we can consider the endomorphism identity minus the pullback along Frobenius as an endomorphism on this group pic prime. And so what does it do? It sends some line bundle together with a trivialization to just this line bundle and then P inverse here. And so of course, I mean, this thing has a canonical trivialization again. And so then the claim is that this is actually an isomorphism. And so given this, we can just define the Borghesian twist as the inverse image of the object I that I've constructed in this example. And just by the definition of its map, it will exactly have the two properties, like the first and the third property, looted over there, if I pull it back to some prism. And so, in the proof, it makes rigorous this heuristic that I've mentioned over there, namely that this infinite tensor product actually converges. Namely, given L, one can set as its unique inverse, one can take the tensor power over all the Frobenius pullbacks of this line bundle. And so one has to see that this makes sense. And this relies on the following. So given any p-nilpotent ring S with a morphism from spiff S spec S to W card, then there exists an I greater or equal than 0 such that for all I greater or equal than I0, the morphism spec of S to W card, and then composed with the I-fold power of a Frobenius, that this factors canonically over the morphism rho from spiff of ZP to here. And so why does this imply the well-definedness of this infinite tensor product? It just, like, to give a line bundle on W card is equivalent to giving canonical, like a line bundle on each S, and this compatible with pullback. And so we have to make sense out of a pullback of this line bundle to S. But the pullback of this line bundle to S, you see that if I is sufficiently large, this pullback along the I-fold power of a Frobenius to here will canonically factor over here. But then, by construction, by definition, this L has a canonical a given trivialization here, and so the line bundle is canonically trivial for I sufficiently large. And so therefore it's just a finite tensor product. Okay. And of course, this construction is natural in S. And so let me indicate how one proves this contracting property of a Frobenius, so to say. Like the contracting property, it says that the Frobenius on W card contracts to this morphisms with ZP to W card.
The diagram is commutative.
Yes.
Why so?
I will show it. Like that's this claim that this I-fold power of a Frobenius factors canonically over this morphism.
You mean that you can choose, because there are different trivializations of different factorization because of the automorphisms in the stack, isn't it?
Yes, and so one also has to choose that even increasing the I, one can also canonically trivialize these automorphisms, like choose canonical isomorphisms. And so more concretely, one has to see the following two statements. So a morphism to the W card is given by some Cartier-Witt divisor, at least locally on S. And so it takes locally the form that it's given by some Teichmüller of A0 plus some Verschiebung of B. And so we know that A0 to the Pi is say 0 for I large enough. And then Fi of alpha is just given by P times the Verschiebung P times Fi minus 1 times B. And so this thing is a unit in the Witt vectors of S, because B is a unit. And so this implies that the multiplication by this element defines a canonical isomorphism, defines an isomorphism between the Cartier-Witt divisor P and the I-fold twist of its Cartier divisor alpha. Okay, this produces some factorization of its morphism, and so one has to take care of the automorphisms. And so that's the following statement. So there exists I greater or equal than 0 such that for all u in the units of S, which are like automorphisms of this point P, meaning that P times u is equal to P, when f of I of u is equal to 1. This means that after when increasing I further, the ambiguity of in choosing these isomorphisms vanishes. And so therefore, one really gets a canonical factorization of this morphism from spec S to W card over spiff of ZP. Yeah. So this is what I wanted to show here. And so now I want to mention this second isomorphism here. So if I restrict this Broykiesian line bundle on W card to the hot state locus, then that's canonically isomorphic to the ideal sheaf restricted to the hot state locus. And so for this, by construction of this inverse via infinite tensor powers, it's sufficient to show that actually for I greater or equal than 1, this Frobenius pullback is canonically trivialized. And so, therefore, it's sufficient to show that the morphism from the hot state locus to W card and then Frobenius to W card, that this factors here canonically over this morphism rho. Because then we can use the same argument, but already the respective I is then actually given by 1. And so these properties follow from the following. So if we take a point in the hot state locus, then we can represent it by Cartesian divisor V of U, where U is some unit. And so then that's equal to a P of U. So we again get the, I mean, we use the just the same argument as over there. And then what one can also use is that the automorphisms of the automorphisms of Cartesian divisor in the hot state locus, they are isomorphic to the F torsion points in the units of W, but this means that they are by definition killed by applying F. And so this then also takes care of the potential ambiguity. And that's what I wanted to say. And this finishes the construction of the Borel-Keesin twist via W card following Drinfeld. And now what I want to present is the approach following Bhatt and Lurie. And here I want to argue that without loss of generality one can assume that the prism is transversal, and so using the W card one can argue as follows. So we want to construct a line bundle on W card, but it's covered by transversal prisms. Like if you take one transversal prism which is non-zero and then consider the corresponding Technev, then all the terms will be transversal, and then it's sufficient to write down a compatible system of line bundles for this Technev with the first and the third property, and then using this property, it's uniquely determined, and it also must agree with the line bundle I've constructed before. So,
sorry. If I remember correctly, Drinfeld has also an interpretation of this in terms of formal groups or something, but does this argument have something to do with it?
Yes. So you mean the construction of a prismatic logarithm, right?
Yeah, just this Drinfeld construction, does that have any?
Like what Drinfeld does using a formal group is that he constructs the prismatic logarithm via the Cartesian stack. So.
Yeah, but I just wonder whether that gives a hybrid, interpretation of this argument.
No, I don't think that the formal groups that Drinfeld considers appear in this construction of a Borel-Keesin twist. They appear in the construction of a prismatic logarithm.
Okay.
And so the second approach, will make this line bundle more explicit, which is also an advantage of this approach. And so Now, given a transversal prism, I want to define more ideals. Namely, I define IR to be I times phi star of I up to phi star to the power R minus 1 of I. So I mean the R minus first pullback of I. And then, of course, because these ideals, they are shrinking by definition, and so in particular we get a canonical morphism from IR modulo IR squared to IR minus 1 modulo IR minus 1 squared. Which is just induced by the inclusion of IR to IR minus 1. And then one needs to prove the following lemma. So first of all these ideals inside A are invertible. And so it's clear that I is invertible, but it's maybe less clear a priori that the Frobenius pullback is invertible, because that need not be flat. So in other words, what one has to show that, say, if I is generated by some element D, then also phi of D is a non-zero divisor. Given that the prism is transversal, then secondly, actually A is isomorphic to the inverse limit over R of the quotient A modulo IR, and then A modulo IR is actually also p-torsion free, and it embeds into the following product. The product from overall 0 s greater or equal than 0 less than R of A modulo phi s upper star of I. And so this inclusion actually has as a consequence this fact that I've mentioned before. So namely, if I consider the fixed points under the Frobenius on AI, meaning this equalizer diagram from before, then this embeds into I mod I squared. I mean that's like now an easy argument using that one has this embedding, and then the phi equivariance implies that implies using this embedding that when actually if an element I maps to 0 here, then it actually must be 0. Okay. So now a third statement is the following. So this projection, it's not surjective, but it's canonically divisible by P. And the map 1 over P times pi R is a map from IR modulo IR squared to IR minus 1 IR minus 1 squared is surjective. And so in particular, this implies that we can define the Borgesian twist. Namely, we can define it to be the inverse limit over R of the following inverse system. So we take IR modulo IR squared, and then as a transition map we take this division of I over P times pi R to IR minus 1 and so on. And so because A is equal to this inverse limit and all these ideals are invertible, that guy will be an invertible A module. And then the reduction of this Prochysian twist modulo I is canonically isomorphic to I mod I squared via the first projection. And then lastly, if I consider the base change of this Prochysian twist to the universal crystalline prism over A, meaning the prism where I join D over P, if, say, I is generated by one element, then this is canonically trivial. And actually, that prism here does not depend on the choice of a generator of D, just because they differ by units, and then this does not depend on this. And so this, this property, of course, is needed in order to compare this construction with the previous one via W card.
But in principle, Greenfield also shows some uniqueness statement, right? For the bundle with these properties. Like once you have a high covariance.
Yes. Like.
So this could be the other way to compare.
No, I think this is how I wanted to argue that if you construct these Prochysian twists via Bhatt-Lurie, you can construct a line bundle on W card with the properties that it has the correct Frobenius, which I have to introduce later, and with canonical trivialization, and then by the arguments from before, it must agree with the line bundle constructed by Drinfeld.
So on the previous blackboard, on the top right corner, consequence something phi equal 1 is injected. So why you write phi equal 1 and not phi equal 0? Is it the same? The same statement?
No, I want to consider here the space where the Frobenius of this Prochysian twist acts via the identity.
Equal to the identity, not to okay, I'm sorry.
Hi. And so let me sketch parts of a proof. I mean, the arguments are not, they are like calculations in this transversal prism, and I want to sketch a bit how one can do this. So for the first statement, one can, without loss of generality, assume that I is generated by some element D, and then by the transversality one knows that PD is regular, but this implies when that P and say any R-fold Frobenius of that thing is also regular, but this then implies by completeness of a prism that also phi R D P is regular, but this implies then that phi R D is also injective. And so in order to check this this statement, so one needs to see that A modulo IR is actually p torsion free, which follows from this inclusion. And then if one has this p torsion freeness, one can just check this modulo p. And there, modulo p, these ideals IR are just some power of I. and then it follows from I-adic completeness. And so for the rest, I want to assume for simplicity that I only give the arguments for r equals 2 in order to simplify the exposition. And I also assume that I is generated by some element d. And so now let me take some y which is of the form phi of d times x. And then of course phi of d times x is congruent to p times delta of d times x modulo I. But this implies, so if y is contained in I, then d must divide x, right? Because if I is contained in I, then this term here is 0, and then by the p torsion, by the transversality, p, this implies, because that's also a unit, that x is 0 modulo I, and this means that d divides x, but this implies that actually I modulo I squared must inject into this product a mod I times a and then phi star of I as which is a special case of this statement for r equals 2. And so we see that we use this property that delta of d is a unit and the transversality. And so let me also explain, only in the case where r is equal to, where this divisibility by p comes from and this surjectivity. So here, this ideal is generated by the element d phi d. And so if we map this to this ideal, then of course we can rewrite this as d times d to the power p dp plus p times delta of d, and then this is of course equivalent modulo I squared to the p times delta of d. And so here you again see why this divisibility by p appears. And you also see that after dividing it by p, that morphism actually is surjective, because delta of d is a unit. And then the general case follows by some induction. And so the fourth claim, and this is clear because if we define this as an inverse limit, then we actually know that if we reduce the Bragg-Hessian twist modulo IR, then we just get this factor IR modulo IR squared. And so for the fifth statement, let me note that by definition, if I take IR and base change it to the to this prism where I join d over p, then this is just given by p to the r. Just because one forced that in this prism one could choose d to be equal to p, and then that's just given by p to the r, and then via the map 1 over p, this of course maps to like p r minus 1 modulo, like which is equal to r minus 1 times that thing, and then modulo I r minus 1. And so one sees in this crystalline case one has the canonical generators PR and PR minus 1, and then this transition maps exactly matches them up, and so one gets the canonical trivialization. And so this finished the sketch of a construction of a Bragg-Hessian twist. And so
Why is it generated by P2?
this one? in this prism, you know that phi, that I is just generated by P. And so when what is phi of that guy, it's also generated by P. And when we took the product over R copies of, where's the definition? Of I here, and so we just get the I degenerated by P to the R. Yeah.
Okay, so you're actually using, for example, Px minus d equal to 0, and then you are
I'm just using that, yeah.
Like if you take d over t, like,
yeah. So P and D after the space change generate the same ideal.
and also there is a d missing in here. Up above. No, just PD times delta d.
Where's? Sorry?
There is no PD delta d.
But this is happening, you mean this one? That's by I, and so therefore this term vanishes here, everything.
Yeah, the first, but the second there is a d.
Yes. Okay. Yeah, thanks. And so, okay, now let me come to the construction of the Frobenius. And so we want to get a canonical isomorphism from this phi pullback of the Brocchiesian twist to I times the Brocchiesian twist. And so we take, this is induced by the following. So if we pull back IR along the Frobenius, then R minus 1, then this is just canonically isomorphic to I inverse times IR. And so now one can construct the Frobenius out of these isomorphisms. And so more precisely, so one uses the following. So we have IR minus 1. We tensor this over R with A modulo phi star of IR minus 1. And so this guy here is isomorphic to phi upper star of IR minus 1 modulo IR minus 1 squared. And so by this isomorphism, this is also isomorphic to I minus 1 IR tensored over A with A modulo phi upper star of IR minus 1. And so now one can also rewrite this term as I inverse of IR tensored over A with A IR tensored over A mod IR to A mod phi star of IR minus 1. So here I'm using that IR is contained in this ideal. And so then this guy also defines I inverse of the Brocchiesian twist, but then base change from A to A phi upper star of IR minus 1. And so now, given these isomorphisms, one can then pass to the inverse limit over R. And so, in the last 10 minutes, so I now want to construct the prismatic logarithm. And so this works as follows. So again, without loss of generality, one can assume that the prism is transversal because the universal case is and so we have, let's take some unit which is rank 1 inside I plus 1 plus I, and then the first claim is that u to the power p to the r minus 1 is actually lies in I r plus 1, and then secondly that if I consider the map 1 over p times pi r as a map from r plus I r plus 1 modulo I r plus 1 squared, which is the surjection to I r modulo I r squared, then this maps u to the p to the r minus 1 to u to the p to the r minus 1 minus 1. And so this means that we can set the prismatic logarithm of u to be this inverse system of elements inside the Brachisian twist. And then, of course, now all this stuff has become very concrete, and so therefore it's easy to see then also that the prismatic logarithm is a group homomorphism. And then also that the Frobenius fixes the prismatic logarithm. Okay, so let me prove these statements. So we can use the injection of this quotient A mod IR into the product of A modulo the Frobenius to the S pullback of I. And then, okay, we have to check that the image of that element, guess I should take here that thing, that this element is 0, and that this given element maps to 0 in each of these factors. And so this follows from the following, namely we have phi s of u to the p to the r minus s minus 1 lies inside phi s bar star of I. So by this, I mean in order to check this equality, it's sufficient to show that this guy here lies in I, but this follows because u is congruent to 1 modulo I. And so that term here is just equal to p to the r, u to the p to the r minus 1. And so we've checked that the first property holds. And for the second one, let me set u to be equal to x to be equal to u to the power p r minus 1. And then x is congruent to 1 modulo IR. So that follows from the first statement. And so this implies that 1 plus x plus and so on plus x to the power p minus 1, that this is congruent to p modulo IR, but then I can also multiply by x minus 1 And so this will be then therefore congruent modulo IR squared. And so now I can equate this. This is x to the p minus 1. So that's equal to u to the p to the r minus 1. And so this is p times u to the p to the r minus 1 minus 1. And so we see that this maps, if we divide it by p, exactly maps to that thing. And so this finishes the construction of a prismatic logarithm. And so the fact that it's a group homomorphism just follows from the definition. And also the last point that that it's fixed under the Frobenius just follows. I mean, the construction of the Frobenius there looked maybe a bit complicated, but what is happening in the end is that the Frobenius is more or less the like a diagonal map. And so when we see that phi of u to the p to the r minus 1, that's by definition u to the p to the r plus 1 minus 1. But this is the component that we set in degree r, and that's the component of a prismatic logarithm that we set in degree r plus 1. And so therefore we get that the prismatic logarithm is fixed by phi. And now I think there's one statement missing that I've mentioned in the beginning, namely the concrete identification of the Broykiesian twist in the case there exists a morphism from a cyclotomic prism. And so first, now assume that we have given a morphism of prisms from the cyclotomic one to AI. And then the lemma to be proven is the following. So when the prismatic logarithm, the Broykiesian twist, is equal to A times EA with q minus 1 times EA is equal to prismatic logarithm of q to the p. And so note that in the case that AI is actually this prism, this pins down uniquely the element EA, because we can rephrase this as saying that the prismatic logarithm of that guy is uniquely divisible by q minus 1, and this generates the Broykiesian twist, and therefore by base change, which then also holds for all prisms. And then also phi of A of this element is equal to PQ inverse of EA. And so why does this follow? So let's consider the ideals IR in IR. So these are these powers of Frobenius, pullbacks of I. And so in this case, this just is given by the Q analog of P to the R, which is Q to the P to the R minus 1 modulo Q minus 1. And so this means that we can just define this generator EA via like these generators that I'm given here. And you directly see this formula holds just because this is the term of a prismatic logarithm in IR, and when q minus 1 of course is q minus 1. And so therefore this equality holds the definition, and yes, and this finishes the description of a Broykiesian twist in this case. And yeah, I want to stop here.
Okay, thank you very much. Are there questions?
Logarithm an der Wischkanischen Isomorphism.
And which map? I think never. Right. So,
so what is the reduction to the transversal case? Can you repeat the idea? So how do you know that if you construct it factorially transversal prism, then it defines the logarithm in general?
okay, so yes. So Bhatt and Scholze, they prove first of all that given any prism, one can find a transversal prism with a map to that given prism, and then also they prove that if you have given an element in this group 1 plus I rank equal to 1, that this element in this general prism can also be lifted to such an element in a transversal one. And then what they argue is that like the category of all transversal prisms with a map to the given one is actually sifted, and then this implies then the independence of the prismatic logarithm that you define for this element by naturality from the transversal case.
And if you choose two liftings, then again, you have to consider the element. You know it can be lifted, but there are two. Again, they prove that the category of they prove that the category with lifting of a given x is shifted, something like this.
Yes.
Maybe if it's easy, you could indicate how one can use formal groups to construct the logarithm.
Okay, so the argument of Drinfeld is as follows. So you have the Cartier-Witt stack, and of course over it you also have the Cartier-Witt stack for GM. And so now what you can do is, so GM, I mean that's given by ZP Laurent's Tate series in T plus or minus 1. And so you have a canonical data structure on this. And this implies that you get a morphism from GM times W card to W card of GM. And so then this thing will be a morphism of group stacks, and therefore you can define a group. Now you can, so let's call this F, and then you can look at the fiber of F. And so Drinfeld calls this group G sigma because he denotes the Cartier-Witt stack by sigma. And so now that group, it looks like a bit like GA sharp, and it has a Cartier dual, which Drinfeld denotes H sigma, and that thing is a one-dimensional formal Lie group. And so the relevance of this group is that if you look at the, say, A-valued points of this for a prism, then this picks out for you this group. And so now what you have to therefore construct is a homomorphism from G sigma to like the geometric vector bundle associated to this line bundle. But now Cartier theory tells you that this identifies canonically with the Lie algebra of the Cartier dual tensored with O1. And so now you have to prove that this Lie algebra is canonically isomorphic to the inverse Brocchiesian twist. And the way how Drinfeld argues there, okay, you construct a Frobenius on that line bundle, and this Frobenius will have the property that it identifies, like, you equip that line bundle with Frobenius intertrivialization, and then you know it's uniquely determined by this data, and then you see, you also check that this implies that this, okay, more precisely, if you look at the Frobenius on the like Lie algebra of that thing, this will be canonically isomorphic to I times this Lie algebra, and then you see together with then the constructed trivialization, it must be equal to Lie of H must be equivalent to O of -1, which then constructs the prismatic logarithm.
Okay, more questions? No, then let's thank Johannes for his minute.